Hello everyone and welcome to another video with Mr. M. Today's focus is going to be on vectors, and we're going to see some examples for vectors, in particular forces in one dimension. Two dimensions, which is something new. We'll be introducing the parallelogram rule, and then probably the second part of the video is going to be on resolving a vector into its components. So far we've seen the importance of vectors in physics, and if we look back at the definition of a vector, we've said that vector is a quantity that has a magnitude, a size, comes with a number, but also a direction. And the scalar quantities are the ones that only have a magnitude. And for instance, we've seen mass as a scalar quantity and velocity as a vector, or force as a vector. Now, if we look at the one-dimension example, like A, in this case, we have an object of mass m, and we have two forces applied on this object, one with 40 newtons and one with 20 newtons. And we can see that both forces are pointing in the same direction, to the right. Now, if we want to calculate the resultant force, and the resultant force is nothing else but a force that could replace all the forces acting on the object and still have the same effect, still cause the same result to the motion of the object. So in this case, we want to calculate the resultant of two forces in scenario A, and because both forces are pointing in the same direction, we just need to add them together. So it's 40 plus 20, that's 60 newtons to the right. It always comes with direction as well. In the second scenario, B, where we have one force pointing to the left and one to the right, we need to subtract them, and then the resultant force will be 10 newtons to the left. That's an easy scenario because all forces are in one dimension. Now let's see what happens when the forces are in two dimensions, and then we have an angle theta, from the Greek letter theta, between them. So we have a mass, we have an object m, and we have one force acting on the on this direction, so this is F2, and another one acting on this direction, and the angle between these two is theta. That could be 30 degrees, that could be 45 degrees, 90 degrees. This is a number that can vary. So how do we calculate the resultant force in this scenario? Now what I want to highlight is that, number one, the length of its vector, the length of the green line and the length of the red line represents the size of it, and the arrow is showing us the direction, so nothing is random here. So how do we apply the parallelogram rule, and how do we find the resultant force in this scenario? What I want you to do is basically, I want you to copy F1, so the length of F1, and place it at the head of F2. What do I mean by tail and head? When we have a vector, okay, we have its tail and its head, okay, and that's what I mean. So the arrow, we call it a head, and the end of it, we call it a tail. So I want you to take F1, its length, okay, and copy and paste it basically at the beginning of F2. So I want you to draw this line that is going to be parallel to F1. So what's this? So the white line here is parallel to F1 and has the same length as F1. And I want you to do the same. I want you to do the same for F2. So you take the length of F2 and you start at the end, at the head of F1, okay, and you add this purple line, which is going to be same in length as F1 and parallel, same in length as F2 and parallel to F2. And now the resultant force, and that's what the rule of parallelogram tells us is that the resultant force is going to be the diagonal of this parallelogram. So the blue one is going to be the resultant force. And this is how we draw it. Soon we're going to see an example of how we also calculate that. So parallel to each force, and we place it at the head of the second force, and it's very important that the length is the same and they're parallel to each other, because the this would show that both forces are in the same direction, point in the same direction. So that's what the rule of parallelogram tells us, and it will become much clearer once we see an example. I want to skip this slide for now. So let's go at this example where we have an object of mass m, okay, and we have a force of 3 newtons in this direction, and we have a force of 4 newtons in this direction. So imagine someone pulling it in this direction, in this direction, and someone else pulling in that direction. What would be the resultant effect? What would be the net effect on object M? So as we discussed before, what we need to do is we need to draw a parallel line with the length of F1 starting at the end, at the head of F2. So I'm drawing this line which should be parallel to F1 and have the same length as F1. And I want you to do the same. I want you to do the same with F2. So I'm going to take a line with a length of F2 and start drawing it at the very end of F1. And this is going to be parallel. And this is going to be parallel to F2. Now, according to the parallelogram rule, the diagonal here, the diagonal of this parallelogram, which is going to be this one, is going to be the resultant force. And that's how we draw it. Now the question is, how do we calculate it? Because we need a size and we need the direction. So these are the two things we need. So basically you need to calculate the length of the orange line. And this is where mathematics and geometry come into place. I want you to focus on this triangle here, okay? We want the length of the orange line. We know the length of the green line, this one, which is 3 newtons, okay? And we know the length of the pink line because it's the same length as F2. So this length here is going to be 4 newtons. This is 3 newtons, and all we want to calculate is this side, okay? So, and this is the resultant force. So this length, according to the Pythagorean theorem, is going to be as follows. This is the hypotenuse, right? So I can say the resultant force, RF, resultant force squared, the hypotenuse, should be equal to 3 squared, the green length squared, so one of the two sides of the triangle, plus the second one, 4 squared. And this one will give me 9 plus 16, that's 25. So RF, the resultant force, is going to be 5 newtons. It's going to be 5 newtons, and that's the length of it. So that's the size. So we managed to find the size of it. Now, we're also interested in knowing this angle here, this angle that we call theta. Okay? Now, how do we find this one? And this is where a bit of trigonometry comes into place, and that's where I've written down this SOHCAHTOA, which hopefully your math teacher has also discussed with you. So the trigonometric functions. So this one basically tells you that the sine of the angle theta is going to be the length of the opposite side, so opposite side divided by the hypotenuse. And if we look at our triangle, the opposite side is 4 newtons, the hypotenuse is 5 newtons. And then from your calculator, what you need to calculate is basically that the angle theta is going to be the sine minus 1 of sine minus 1 of 4 over 5, and this will be in degrees. Okay, and that's where you complete your problem of calculation. So you have the length, and then this is how you get also the angle between them, because you need size and direction. So the direction is basically the angle theta. Okay, I hope this was helpful, and we'll see in part 2 how we work on the reverse process.